Welcome back to episode 3. Maya and I are on this journey with you to compare climate changes in the past with the changes we are living through today. Some sources online say a changing climate is normal, but something really doesn't seem quite right to us.
We thought it would be better to analyze the data ourselves and then decide. In the first 2 episodes, we worked with Carly Peltier, a climate scientist who showed us how data from glacial moraines in Patagonia indicated that in the past, the climate typically swung between ice ages and warm interglacial periods every 100,000 years.
Now that we know what climate change looked like in the past, it is time to look for some data that can tell us if the changes Maya and I are seeing firsthand here in California are normal or if something very different is going on. For this episode, instead of looking to glacial moraines in Patagonia, we're going to go to Oregon State University to analyze data pulled from the ice in Greenland and Antarctica.
Let's join another scientist, Jon Edwards at Oregon State, to figure out if the climate changes we are witnessing now really are different from what has happened in the past.
Hi, I'm Jon Edwards. I study paleoclimate and ice cores at Oregon State University. Carly asked me to weigh in on the 100,000-year cycles in climate that you saw in episode 2. For that, we can look to ice cores, and what we find is that those cycles were not unique, and in fact, they occurred over and over again over the last 800,000 years. So the question is, what's causing these 100,000-year cycles in the past? So what we find is that there are really 2 key factors that can explain these glacial interglacial cycles that occur every 100,000 years. The first is something we call the Milankovitch cycles, or the Milankovitch theory, after the scientist who discovered them. And what this is that Earth's orbit around the sun is not always the same. There are subtle changes in Earth's tilt towards the sun, as well as the shape of Earth's orbit. Sometimes it's more eccentric, sometimes it's more circular. Additionally, Earth's tilt towards the sun has a little bit of a wobble to it, and that wobble changes how Earth is oriented towards the sun at different times of year. All these 3 things together cause changes in how much insolation is occurring in the northern hemisphere, which allows ice sheets to grow and to shrink. But Earth's orbit around the sun can't explain everything. Something else must be contributing to Earth's warming in the past. And in episode 2, you saw that carbon dioxide also changes over these glacial interglacial cycles. And that is exactly the key. But where did that carbon dioxide come from during interglacial times, and where did it go during glacial times? For that, we can look to the ocean. And so it turns out that the ocean has the ability to absorb large amounts of carbon during glacial times, and then release that carbon in the form of CO2 back into the atmosphere during interglacial times. This happened over and over and over again over the past at least 800,000 years or more. So historically, over the past at least 800,000 years, these are the 2 key factors that have caused changes in Earth's climate. Changes in carbon dioxide going into and coming out of the ocean, and changes in Earth's orbit around the sun. What's different about the changes that we're seeing today compared to the changes that we see in the past? For that, we're going to drive back to the lab and analyze some data. All right, hello again, and welcome to Oregon State University. This is where we have the OSU Ice Core and Geochemistry Lab, where we make a lot of the measurements you've seen. We also make a lot of measurements from marine sediments, and from these we can learn a lot about not just what happens at our poles, but also in our oceans and around the globe. All right, welcome to the Oregon State University Ice Core and Geochemistry Lab. This is where all the magic happens. We take ice cores from Greenland and Antarctica. We sample those ice cores and we take that ice and we either crush it or we melt it to liberate the gas. So we can then measure it for things like carbon dioxide, for methane, for different isotopes as well as other greenhouse gases. And so there's a lot happening here. You might have already met some of the people who work here, such as Katie, Ben, and Sebastian, who make a lot of these measurements. So this is the lab where we make those measurements of carbon dioxide from ice cores. Oregon State University is also well known for measuring sediments from the ocean, which can tell us about past temperature changes at a global scale. This is done in labs just upstairs from here. All right, so we can use the data measured in this lab, as well as what's done in the sediment labs upstairs, to answer that question that Carly was asking. How does the climate change we see today compare to the climate change that we saw in the past? So one of the key differences of the climate change that we see today and the climate change that we saw in the past is the driving factors. In the past, as we mentioned earlier, the driving factors were changes in Earth's orbit around the sun and changes in how much carbon dioxide is being either absorbed into the ocean or put back into the atmosphere from the ocean. Today, the climate change that we see is due to us. The increase in carbon dioxide is from burning fossil fuels that formed millions of years ago. And we're putting that carbon dioxide back into the atmosphere by using cars, by burning coal and coal burning power plants, by producing cement. All these things contribute to increasing carbon dioxide in our atmosphere. And again, that carbon dioxide came from fossil fuels that formed millions and millions of years ago. This is fundamentally different than what we saw in the past, where the carbon dioxide was coming from the ocean and going back to the ocean during glacial interglacial cycles. So we're going to use data measured here at Oregon State to compare the changes that are occurring today to what we saw in the glacial interglacial cycles of the past. One way we can do this, we can look at the rates of change as we came out of the last glacial period into the interglacial period in carbon dioxide. We can also look at the rates of change in temperature coming out of the last glacial period and into the interglacial period. We can compare those to what we're seeing today. So for this, let me pass you on to one of my climate friends, Jack, at Stanford University. He's going to walk you through the calculations to determine rates of change in the past and rates of change today.
Thanks, John. If we're going to calculate rates of change, we will need to record some data in your notebooks. So on a blank page, let's make a data table.
We will look at two different climate periods. First, we will look at the warming that took place after the last ice age. Scientists call this the last glacial maximum, or LGM. The second climate period we will look at will be the one we're living in today. We will call this the period of climate alarm.
For each climate period, we will calculate the number of years as well as the level of carbon dioxide in the atmosphere. We will record the carbon dioxide level at the beginning and the end of each period and use those measurements to calculate the change.
In the last column, we will calculate the rate of increase in carbon dioxide in the atmosphere during each period. We will calculate the rate of increase by dividing the number of years by the amount that the carbon dioxide level changed.
Here are the carbon dioxide levels in the Earth's atmosphere after the last glacial maximum. This data was pulled from gas bubbles trapped in the ice cores that John showed you earlier.
I'll draw a best fit line through the period where the climate warmed after the last ice age. We will analyze the carbon dioxide levels between 18,000 and 11,000 years before present. This climate period spans 7,000 years.
We can use the graph to find the carbon dioxide level at the beginning and the end of this period. It looks to me like at the beginning, carbon dioxide was about 188 parts per million. At the end, it was about 270. This means that carbon dioxide increased during this warming period by about 82 parts per million.
The goal of all of this is to calculate the rate of change. If we divide the 7,000 years by the increase in carbon dioxide, I calculate the rate of increase at about 85 years per parts per million.
I think it helps to turn this data into a story. The story that this number tells me is that at the end of the last glacial maximum, it took about 85 years for the oceans to add 1 part per million of CO2 to the atmosphere.
So that is the technique we will use to calculate the rates of increase. Let me bring up carbon dioxide levels from the current period of climate alarm, and you can give the analysis a try yourself. Pause the video, analyze the graph, and calculate the rate of increase in carbon dioxide. Don't forget to write your own climate story. When you are finished, hit play again, and we will see how our numbers compare.
Welcome back. Let's see how our numbers compare. I count 25 years between 1995 and 2020. I estimated the carbon dioxide level at 361 parts per million at the beginning and 414 at the end, for a change of 53 parts per million. Plugging these numbers into our rate calculation, I got about 0.47 years per part per million.
The story I see in these numbers looks like this. During my lifetime, burning fossil fuels is adding 1 part per million of carbon dioxide to the atmosphere about every 6 months.
Let's do the same type of calculation for the temperature on the planet during the same time periods. Our data table will look pretty similar, except instead of carbon dioxide, we will calculate the rate of warming during each period.
Here is the temperature graph for the warming period after the last glacial maximum. I'll add the best fit line through the warming data and then let you pause the video to calculate the rate of warming for this period. When you are done with your calculations and writing a temperature story, hit play and we can see how our numbers compare.
Welcome back. Let's see how our analysis of the data compares. The warming period is still 7,000 years. Scientists reference temperatures to the Earth's average over time. How far the planet is from the long-term average is called an anomaly. I estimate at the beginning of the last glacial maximum warming period, the planet was about 6.1 degrees Fahrenheit cooler. At the end of the warming period, it was only about 1.1 degrees cooler than average. The rate calculation shows that it took about 1,400 years for the planet to warm 1 degree Fahrenheit during this period.
Our story would say that when the planet warmed after the last ice age, natural processes like changes in the Earth's orbit and oceans releasing carbon dioxide warmed the planet 1 degree Fahrenheit every 1,400 years.
Let me bring up a graph showing how temperature has changed during our current period of climate alarm. We have already drawn a best fit trend line through the data. Go ahead and pause the video and analyze the rate of temperature change for this period. When you are finished, hit play and we can compare.
Welcome back. Let's see how our data compares. I calculate 25 years of time between 1995 and 2020. The temperature over that period increased about 0.95 degrees Fahrenheit, giving us a rate of about 26 years per degree Fahrenheit.
This tells quite a different warming story compared to the end of the last ice age. This tells me that during my lifetime, carbon dioxide from burning fossil fuels is trapping heat energy and warming the planet 1 degree Fahrenheit only every 26 years.
Well, those 4 graphs give us quite a bit to think about. To finish up, I would like you to pause the video once more and write down 2 things that you noticed when looking at this data and 1 thing that you wondered. When you are finished writing, hit play again and we will share some final thoughts about our current changing climate.
Welcome back. So Carly asked us 2 key questions. How did climate change in the past? And how does climate change today compare to climate change in the past? So we learned earlier that the climate change in the past was due to two key factors: changes in Earth's orbit around the sun, which we call Milankovitch cycles, and also, secondly, changes in CO2 going into and coming out of the ocean. This is different than today, where carbon is being put into the atmosphere by burning of fossil fuels. The second question Carly asked us was, how does climate change compare today to what we saw in the past? We just did that calculation. We looked at how quickly climate was changing in the past, how quickly carbon dioxide was rising in the past as we came out of the deglaciation, and compared that to how it's changing today. A couple of things I noticed about the data that I find quite remarkable is the magnitude and the difference of climate change in the past compared to how the climate is changing today. During the warming of the last glacial maximum, the oceans slowly released carbon into the atmosphere at a rate of about 1 part per million every 3 human generations. Today, humans are burning fossil fuels at a rate that adds more than 1 part per million in just a single school year. That is a gigantic difference. 3 generations compared to 1 school year. The second thing I notice is the impact of all that additional carbon dioxide is having on the temperature of our planet. After the last glacial maximum, the warming that took place was due to the Milankovitch cycles and the little bit of carbon dioxide coming out of the oceans. Those driving factors warmed the planet about 1 degree Fahrenheit every 1400 years. That means the planet warmed about 1 degree between the fall of the Roman Empire and when I was born. The climate change we're experiencing today, driven by the carbon dioxide being released from fossil fuels, has heated the planet more than 1 degree Fahrenheit in just my lifetime. It is really hard to actually comprehend the magnitude of the difference between the natural climate change cycles in the past and the climate change we are living through today. One thing I wonder is, what will this changing climate mean for my kids as they get older, or my grandkids? What species will be able to adapt to the rate of change in Earth's climate that we're seeing today? I'd like to be optimistic in thinking about our ability to tackle problems, and the climate crisis is certainly a big one. Together, I think we can work together to mitigate the worst consequences of climate change. With that, I would like to send you back to Carly for her final thoughts.
Thanks for that analysis, Jon, and thanks for sharing your hopeful outlook for our future. So we started out this series using data from rocks deposited by glaciers in Patagonia to figure out what climate change has looked like in the past. We also got to see how much faster the climate and atmospheric CO2 concentrations are changing today than they changed as the climate was warming out of the last ice age. And so now you have gotten to be a part of showing that the climate change happening today is happening at a truly alarming and unprecedented rate. The good news is that if we act up right now, we can avoid the worst of climate change. So my opinion is that this is a really special moment in time. We have a lot of power as young people living on the earth right now to determine what the next few hundreds or thousands of years will look like on planet Earth. Each of us has the opportunity to be a part of the solution and to help put us on a better path forward. So I came up with 3 specific things that I think could be really impactful. But I hope that you'll go ahead and see if you can come up with some for yourself. My first idea is that if you're not already part of one, join a climate justice or action group at your school or in your local area. There are tons of groups across the country that are doing really awesome, impactful, and fun work. My second idea is to see if you can help your school make energy efficiency upgrades. So there are federal and state programs with funding to help public schools do this right now. See if your school can join the Efficient and Healthy Schools campaign or another program like it. My third idea is to just keep learning about the climate crisis, talk about it with your friends and family, and think about how you can go into a clean climate career. I am actually in DC this year working with government to help make progress towards climate solutions, and I really hope that you will join me in this work.
So thank you very much for joining this virtual field lab series. I had a lot of fun, and I hope that you did too.
Do you have any ideas for how we could actually slow down that increase in carbon dioxide to our atmosphere?
Don't waste food. Don't drive when you can walk. Don't drive unless you have to. Use layers instead of turning up the heat, and use a fan instead of a.
That is absolutely fantastic advice for my generation, for your generation. I like to be an optimist. I like to think that we can solve this crisis together. All right. Thank you. And now I'll send it back to Maya and Jack.
3, 8.
You don't need to hold it up anymore. We know which scene it is.
Just to be sure.